I recently was speaking to somebody about knowledge bases, and I realized that the person was unfamiliar with embeddings and how they work to help us use knowledge bases. And so today I would like to go over what an embedding is in the context of a knowledge base and why it's so useful to understand. So let's start with this chart right here. This is an expression of terms and they're relational to one another. So I can cruise over it. I can zoom in and see the relationship of these things. Let's just highlight maybe like a little section here. Okay, interesting. Let's zoom in. So we got demons, evil, paradise. Wow, these things all look really tightly clustered for a good reason. If I zoom out and click over here, see what we get. Okay, belt, colors, mask, interesting. Cool. So how are we able to project these kinds of things into this space? Obviously, with space, things are extended in space, which suggests that they have some kind of value for an axis. So you can see there are these three axes here. This is a three-dimensional space. So you have the X and Y, and then the Z axis. So you would think that each one of these coordinates would have three values: where it falls in the X, where it falls in the Y, where it falls in terms of Z, the depth, right? And that is a way where we can say that things are either close together or far apart. Right? So we have this sort of this way of being able to spread things out and cluster things and contrast things by some kind of measure. If we dial it back and just think about vectors generally, we can see here, like we can point them in directions. Now, this is a 2D space, right? I can say these vectors are very similar in direction and magnitude. Let me make this a little bigger. These two vectors are very similar in direction and magnitude. These are very different. These are orthogonal, 90-degree angle, so neutral. They're not dissimilar. They're not similar. They just don't have a lot in common. Now I can express how similar they are by taking the dot product between these two. Now you'll notice that these vectors have two values, the X and the Y, and that's why we can put them on this chart in this way. We can use mathematical operations, I'm going to zoom out a little bit, to say what's the difference between them? Or if I add them together, what would it look like? I can also take the dot product. How similar are they? In this case, I have this value here. Let's see what happens if I move them. So these should be more similar, right? So we should get a bigger number. Yeah. Let's see what happens when we say they're 90-degree angle. Ooh, pretty close to, okay, not so similar. What if they're opposite? Okay, very dissimilar, very small number. Okay, so that's how these are designed to work. Now, language is extremely rich. There are all sorts of dimensions. So if we talked about a horse is on a chess set, in a chess set, there are all sorts of kinds of horses in old Western films. A horse, stop horsing around. All these ways that we use horse communicates that, geez, horses really fit into our language in all sorts of ways. Now, it seems unlikely that I can create a 2D vector that really can express the richness of a horse. And that's why embeddings come along. Embeddings are high-dimensional expressions of language. So let's take a look. I have this embedding workbook. Let's see if I can make it a little bigger. Okay, we're just going to do some imports here. Let's cruise down. And we have these 4 lines of text. Hello world. That's what you learn that's what you print when you first learn Python. So that's going to be really similar to text number 4. Everyone can learn Python. And then there are these two in the middle. And they should be pretty similar because they both have to do with GenAI, right? Prompting and RAG. We have these 4. Some are long, some are short. In this case, we're using tokens. Tokens, they're on average, according to OpenAI, there are 4 tokens that make up one word. If you want to see what tokens look like, you can go to OpenAI's tokenizer and you can write something like hello world. And here you can see there are 4 tokens. And see how they fit together? There's a little space before word. And that allows this token to fit with other tokens. Okay. Let's go back to our workbook. Okay, now to be able to generate an embedding, we can use an embedding model. In this case, I have this ADA 002. And we're going to take the text and we're going to generate those embeddings. Okay, now what do they look like? They're really long. They have a length of 1,536 dimensions. Now we say indices. So this is the beginning index here. And then there's index position 1, 2, 3, all the way to 1,500, just about. Right? So here's hello world's vector. Here's prompt engineering is critical for LLMs to function well vector, and so on. Now, what would these look like if we just if we put them on a line and then the negative values went down and the positive values went up? Well, you can visualize these in that way, and here they are. So think of these as the fingerprint that these expressions have in our language, right? So this is how they can essentially be expressed, and because of numerical, they can be compared, contrasted. So if I scroll down, we'll see how we can project these into 2D space. We're just using some clever math, something called PCA. And we can see that hello world shares the same side as everyone can learn Python, and the GenAI stuff is on the right-hand side. Now this is all relative. Don't pay attention to the bottom or left axis. We're essentially projecting these really long vectors into a 2D space. If we scroll down, this formula is how we can start to express how they're similar. As I mentioned before, these can be projected into a space, which means that with the x-axis, the y-axis, or I guess there's 1,500 axes here, you would express the vector, and you could say how close, if I were to project these very long vectors into space in that way, where every index provided a kind of dimensionality to the expression, how similar would they be? And so we're going to loop through all of them and see how similar they are. And here you can see hello world is most similar to everyone can learn Python. And then these two, they have to do GenAI, are also the most common. Now, why do I care about this? How is this useful for using knowledge bases? What if you run a query and you say, hey, what is RAG? And you want to augment your prompt by retrieving from your knowledge base the most relevant pieces, chunks of documents across your knowledge base. The way to do that is to do a similarity search. How do you do a similarity search? You basically generate embeddings for everything in the knowledge base. You then generate an embedding for your query, and then you do a similarity search. So let's take a look at how RagPlay does it here. Here we have all the chunks in our knowledge base, and I want to ask, what is GenAI? And you'll notice as I continue to write, the similarity searches return different chunks that are considered to be more and more relevant, right? So that's how embeddings are useful for pulling in information from a knowledge base. And it all comes down to vector or numerical representations of language. Hope you enjoyed this video. Please drop any comments and reach out if you have any questions.